Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On. In this tutorial video, we'll go through this November 2015 paper 2 variant 1 for the Cambridge International 16 to 18 years old A-level curriculum. In this first question, we have aluminium. Aluminium is very clearly a metal in period 3. These days we use the term group 13 for the new specification from 2016 onwards. And we are asked to describe the structure of solid aluminium. So we know that it has a giant metallic structure. So as a solid, you will have particles tightly packed together. You got to define and specify what kind of particles that is. So we first talk about the structure first, giant metallic structure. And what does the giant metallic structure consist of? It consists of aluminium cations that you get after you shed away, after you lose your outer shell electrons. So you get aluminium cations, Al3 plus, in a sea of delocalized valence electrons, because that is what you do as a metal. You shed away your outer shell, your valence electrons, and it is that electrostatic force of attraction between the valence electrons as well as the positively charged cations that result in the strong metallic bond. So what else can I say? Sea of delocalized valence electrons, that's pretty much it really, I can say. What else can I say? I think the idea of solid there is that I have to talk about solid particles as well. So in the solid state, the particles, in this case the ions, the cations, they are arranged like in a layered structures. They are tightly packed. So this is a little bit of state of matter as well. We just don't want to lose any mark at all. They are tightly packed in a fixed position, so they are not free to move at all. However, metals does conduct electricity, not because of the cations as they don't move. It's the delocalized valence electrons that are delocalized and therefore they are free to move around. In part B, a common use of aluminium is to make as conducting cables. Obviously, they conduct electricity. So suggest two properties of aluminium that make it suitable for this use. This is straight from the 14 to 16 years old IGCSE, GCSE or O-level curriculum as part of the uses of aluminium. I think these days in the new specification, we don't talk too much about the use of aluminium anymore, as they've taken out the extraction of aluminium from aluminium oxide from the A-level AS syllabus. But regardless, it's still a very good question. I mean, we talk about the light weight or light density or the low density. Light, low, that should be all right. Light or low density of aluminium is also the primary reason why you use aluminium as a major component to make a aircraft body. So it's light. And then the other one is that it has high conductivity. So across the third period, we know sodium, magnesium, and aluminium. Aluminium is the best conducting as it can delocalize the greatest number of valence electrons, giving the Al3 plus cations there. Okay, straight to the point there. Now the cables are attached to pylons by ceramic support. Again, ceramic material was from the 2015 syllabus and it has since been taken out. But ceramic materials must have giant structure. So we don't care about, it's not necessarily one particular type of giant structure, because it could have giant ionic, it could even be giant molecular, because the type of materials that are considered ceramic, SiO2, what else, MgO, if I'm not mistaken, Al2O3 as well. So must have giant structure that can withstand high temperature, because they don't melt or boil easily. Okay, high temperature. So electrical cables carry electricity. Sometimes you get heating up due to a power surge, and you don't want these things to melt easily or to boil easily, right? So they have high melting point. They don't melt easily. They have high melting point. They don't melt easily. That is saying the exact same thing there. Okay. What Well, I guess actually they don't melt easily must be the next part of the question, because what makes it suitable for this use, they don't melt easily. Whereas describing the structure of ceramic materials, so must have giant structure, that's probably the way to get around these two questions here. But just take note that ceramic was already taken out from the syllabus from 2016 onwards. Now the next thing, aluminium reacts with chlorine to give you this white solid chloride. This is part of period 3 chloride chemistry under AS periodicity. So this is still in the syllabus, obviously. All right. Describe the structure and bonding, and then suggest how it explains the low sublimation temperature, solid going to gas. So the low sublimation temperature suggests that you must have a simple covalent structure. That's the only structure that will have low melting and boiling point, because you would just be breaking the weak intermolecular forces between the molecules. So the low sublimation temperature straight away suggests to you it must have simple covalent structure or simple molecular structure, both of which are accepted by Cambridge, obviously. Suggests that the chloride, the solid chloride, has simple covalent structure. And when you have simple covalent structure, what do you break when you have to boil it or melt it? So we talk about sublimation. So what I can say is, so sublimation only need to break. So there's solid going to gas, only needs to break or overcome weak intermolecular forces. We have to use all the right and the correct adjective in order to describe this thing, so that we don't lose any marks at all. And this intermolecular means between the molecules, but it doesn't hurt to add in this idea that this intermolecular force of attraction is not inside the molecule, it's between the molecules there. So if you only need to break that weak intermolecular force of attraction, so this doesn't require a lot of energy. This does not require a lot of energy. So the very idea that we need to relate energy expenditure with how easy it is to melt or boil, or in this case sublime, is going to be how you explain it fully, and not just stopping there without making a qualifying statement usually. The next question, calculate the empirical formula. So this is defined as the simplest whole number ratio of atoms. Simplest whole number ratio of atoms. Straight away from your O-level or GCSE or IGCSE level chemistry, we have 79.7% of chlorine. This is percentage, and percentage is out of 100%. So this is called mass per 100 gram, because it's essentially the breakdown of the percentage. If you have 79.7% of chlorine and you are a chloride of aluminium, therefore your remaining percentage must be the other atom, which is aluminium. So 100 minus 79.7, I get 20.3. So going back to that, if I have mass, I need to work out my mole. So my mole there is mole of the atoms. So I need to go to my periodic table. So in the new 2022 syllabus onward, your periodic table will no longer be on a separate data booklet. They'll be inside the question paper itself. So, learn to cope with that. Aluminium, 27.0 is the relative atomic mass. And then I am doing relative atomic mass because of the definition, simplest whole number ratio of atoms. So I don't do the molecular mass at all. So 20.3 divided by 27.0. I get 0.752. 79.7 divided by 35.5, I get 2.25, like that. So what next? Well, I need the simplest ratio, right? Because it's the simplest whole number ratio of the atoms, so the aluminium and the chlorine. To get the simplest whole number ratio, you need to divide by the smallest number, which in this case is 0.752. So that divided by itself is 1. That divided by 0.752, that gives me 2.99. Simplest whole number ratio of the atoms, AlCO3. Of course, as you know it, trigonoplanar geometry, 3 bond pair, 0 lone pair, they repel equally, the 3 bond pair repel equally. what you get is trigonoplanar. This is as stated in the VSEPR, valence shell electron pair repulsion theory from AS chemistry, structure and bonding, shape of molecule there. And the next bit is this sample of this chloride, meaning to say in the vapor phase, in the gaseous phase, they occupy this much volume. And they give you the temperature and the pressure. It seems like this is an ideal gas equation kind of thing. In our ideal gas equation, P equal to nRT, and that N refers to mass over mR for the gas. If I want the mR, I have mRT over PV. It's always been my habit in all my tutorials, and you can see this from the topical playlist, that I rearrange to get what I want, and then I write down all the detail on the side instead of wasting time putting them in. I clarify everything on the side so that I'm not making any mistake when I key in my calculator. 8.31 joule per Kelvin per mole or joule per mole per Kelvin is stated in the data booklet, which of course now will be provided in the question paper itself from the 2022 syllabus onward. The temperature of the gas must be in Kelvin. This is in degrees Celsius given there, so I have to add it with 273. I get 473 Kelvin. My pressure is in kilopascal, so I have to convert this to pascal by multiplying by 1000, so times 10 to the 3 pascal. The very last thing, which is a bit tricky, is this volume here is in cm cube. So you know, if our volume is in cm cube, we think about 1 cm is 1 divided by 100 meter, because you convert cm to meters like that. So I can think of my indices 10 to the minus 2 meter. If you cube both sides, because that is what primary school mathematics will have told you, equal mean whatever you do on the left, you do it on the right. So when I cube both sides, I get 1 cm cube. 10 to the minus 2 cube, your mathematics will have told you, that's 10 to the minus 6. So to convert cm cube to meter cube, I need to multiply by 10 to the 6. So the volume there is 200 times 10 to the minus 6 meter cube. I better write down the unit properly, otherwise I'll make a mistake. I've got all of these in the correct units now. I've got the expression, so I don't really need to write them down again. I already done the hard work. I already specified to the examiner I know what I'm doing. I just need to press my calculator now. 1.36 multiplied by 8.31 multiplied by 473 divided by 100 times 10 to the 3 divided by 200 times 10 to the minus 6. Make sure you know how to key this into your calculator, obviously. And if you get a silly number in the end, they want 3 significant figure, so you know, I'm just gonna show it to 4 first. So 267.28, there's 5 significant figure, but last but not least, you want it to 3 significant figure. So that's it really, 267 my final answer there. So 267 as required, 3 significant figures. To get the molecular formula, we know the MR of the empirical formula multiplied by a certain factor will give us the MR of the molecular formula. So our empirical formula just now was AlCl3. So if you go to the data booklet, your periodic table, 27.0 plus 35.5 times 3, I get 133.5 times a factor, let's say x equal to 267. So that looks like it's a multiple of 2. And if that is the factor, 2 is not the answer because they want the molecular formula. Definition of molecular formula is stated in the AS syllabus. It was also stated in your year 9 chemistry when you were 14 to 16 years old during the O-level, IGCSE or GCSE level chemistry. So it's Al2Cl6 because you got to multiply the empirical formula by a certain factor. So there are 2 of that and there are 6 of that, as you have 2 multiple lots of this empirical formula. Al2Cl6 is a case study under your dative covalent bonding part of the syllabus, and what you can do is you must be able to draw. You must be able to draw because they can ask you to draw the dot and cross of these, and before you do the dot and cross, you need to be able to do the display formula so that you know which one is the dative covalent bond, and that is what I've done there. There's the dative covalent bond, the pink one there, and the rest of them, they are all the normal covalent bond. When you convert this to dot and cross, you will have 2 lone pair remaining on these 2 chlorines because you have used one of the lone pair on each chlorine to form a dative covalent bond. The arrow comes from the donor to the acceptor. The one with the lone pair donates both the electrons to this aluminium with the empty orbital. As aluminium is in group 13, only 3 valence electrons. Just now, you had trigonoplanar geometry because you have 0 lone pair and 3 bond pair, since aluminium has only 3 valence electrons there. So everything kind of linked together. When you draw the dot and cross, also do not forget that there are 3 lone pairs on this other chlorine and 2 lone pairs on this chlorine. And yeah, make sure you know the dative covalent bond, that you don't show a dot and cross, you show both the electrons coming only from one of the atom, as defined in AS, dative covalent bond, also known as coordinate bonding. Okay, that's the end of that 13 mark. Very nice first question here. In this second question, explain the meaning of the term enthalpy change of formation. You will notice that they don't mention standard here, so you don't get 1 mark for standard conditions because they do not mention standard here. Sometimes they will say explain the meaning of the term standard enthalpy change of formation, but if you already remember the definition, if you say understand the conditions, I don't think they'll penalize you. You just don't get the extra mark or extra credit awarded for it. Okay, so what can we say? Enthalpy change of formation is definitely enthalpy change. So it is not the process. Be very careful. A lot of students say, oh, it's when 1 mole of blah, blah, blah. But this is enthalpy change. It is not a process. It's the enthalpy change for the process. So always be careful with your use of words instead of jumping in straight away. So it's the enthalpy change when you form 1 mole of a substance. So when 1 mole of a substance is formed, from its elements, it has to be formed from its elements, and everything must be in their standard state. Everything, including the reactants, including the substance you are forming, must be in their standard state. And sometimes the definition will say define standard enthalpy change of formation. So usually you will say under standard conditions. Seems a bit repetitive, but when you have a 3 marks definition, you probably get 1 more marks for the standard conditions, which will be 298 Kelvin or 25 degrees Celsius and 1 atm pressure. So I've simply included the standard condition here, even when they don't ask for the standard, because we don't know when they will give you 3 marks and when they will ask for the standard enthalpy change of formation. So it's good to always remember the standard conditions, but even if you write it down here, they don't ask for it, you just don't get additional credit. I suppose the 2 marks are from here, 1 mole of substance from its element, and the other one, everything in standard states there. Now next one, give the equation for the reaction. So you want the standard enthalpy change of formation of liquid sulfur trioxide. Be very careful, liquid. That's what they say, liquid. When you are asked to do enthalpy change of formation, always write the product first because of the definition, 1 mole of this substance. This is the state that you want. So now you're forming from the element. So sulfur as an element, and then you will have sulfur as a yellow solid, and then you have oxygen gas. And then you will have 3/2 oxygen gas because you only want 3 oxygen atoms, and oxygen exists as a molecule, they don't exist as an atom. So the elemental form of oxygen from its element as oxygen. If you decide to use S8, because sulfur can exist as a molecular form, which is S8, if you use that, then you will need 1/8 of that, so that you get 1 sulfur, so that you are forming just 1 mole of this SO3. Okay, and includes that symbols, so you have to have the correct stat symbols, including this one must be liquid, cannot be gas because of what the question specified. This next question, it says use bond energies from the data booklet. Well, now that you have the 2022 syllabus where the data booklet is no longer a separate entity, but rather it is included in the data booklet, so things will have changed. They might have provided you with the bond energy here. So if we are given the bond energy, everything is in the gaseous state, we can use delta HR equal to the total energy for bond breaking minus the total energy for bond forming. So it must be the total energy for bond breaking minus the total energy for bond forming. So what are we breaking here? We are breaking a nitrogen-nitrogen triple bond. So we have 1 times 944 for the nitrogen-nitrogen triple bond. We are breaking 3 mole of these hydrogen-hydrogen single covalent bond. So there's 3 times 4, 3, 6. We close the bracket because there's everything we need to break, and then minus everything we need to form. We have 2 times NH3. Now this is the confusing bit for a lot of students. 2 times NH3 means I would have 3 NH bond for 1 NH3, And then I have another NH3. So altogether I have 1, 2, 3, 4, 5, 6. So I'm forming 6 times NH bond. So be very careful. NH bond is heterolytic between 2 different atoms. So we're looking at the different part of the data booklet. Not too sure how the new syllabus specification would give you in the question paper. Because if they print out the whole data booklet inside the question paper, it's going to be quite thick. So I guess they'll be very selective in terms of what data they will ask you. And it can probably restrict them, or probably not, in terms of the question they can ask you. All right, so 2256 minus 2340. Your calculator show you a negative, which is okay. But then, sometimes your enthalpy change is positive, and you have to learn to interpret a positive enthalpy change with a sign, a value, and a unit for obvious reasons to get the full marks. The next thing, state the essential operating conditions. As you know, Haber process operates under 3 individual conditions, even from your IGCSE. GCSE are all level days. So first one, you use finely divided ion catalyst. This is to increase the surface area of the heterogeneous catalyst, because this catalyst is in a solid phase, is a different phase, different state as your gaseous reactants. These are definitions stated in the AS rate of reaction topic. Now in terms of temperature, so we have a temperature of around 400 to 500 degrees Celsius. Somewhere along that line is the generally accepted convention. We also need a high pressure of around 200 to 300 atmospheric pressure. Whether it's for exactly 200, 300, I'm not entirely sure, but I know it's not at 1 atmospheric pressure. It's a very high pressure, relatively high temperature, and then a finely divided ion catalyst there. As for the next question, there are 4 marks altogether. This is about the choices of temperature and pressure. So first of all, you need to think about temperature and then pressure. The choices always come down to 2 things, rate versus equilibrium. This rate versus equilibrium is always a very popular question. Of course, the question doesn't say rate versus equilibrium, but when I say that, what I mean is rate versus amount. Equilibrium refers to this equilibrium yield of the ammonia, which is your product. As a chemical engineer, your goal for your boss is to produce as much product at the lowest possible cost. This forward reaction is exothermic. You see, we talk about forward reaction being exothermic means that it releases heat energy. So based on our calculations, the forward reaction to make ammonia, to form ammonia, is exothermic. So that means it releases heat energy. So high temperature, when you increase temperature, what would the equilibrium tries to do? High temperature means the equilibrium or the system will try to lower the temperature, will want to decrease temperature, but you only know how to release heat because that's what you do in the forward reaction, releasing heat energy. If you want to decrease temperature, do you want to release more heat or do you want to release less heat? Well, to get lower temperature, you will release less heat, and by releasing less heat, therefore the equilibrium will shift to the left, and when you shift to the left, you will have lower yield of ammonia. That is not good at a high temperature. So what can we do to counteract this? So do we want as low temperature as possible in order to go to high yield of ammonia? Of course not, because however, too low temperature will make the reaction very slow. So 400 to 500 degrees Celsius is the best compromise. So I've written quite a lot there. You can probably summarize it a little bit and get straight to the point. So now in terms of the pressure, so high pressure will mean greater collision frequency. It will mean the reacting particles, they are much closer together. And when they are closer together, they can collide more frequently. And when they collide more frequently, the rate of reaction will be faster. So faster rate of reaction due to the higher collision frequency. Last but not least, we must also talk about equilibrium yield as well in terms of pressure. Because of the compromise we make on the temperature, the high pressure there would shift the equilibrium to the side with lesser gaseous molecule. You have 1 and 3, you have 4 moles of gases on the left as reactants and 2 moles of gaseous reactants, 2 moles of gaseous products. So when you increase pressure, your equilibrium tries to decrease pressure. When you try to decrease pressure, it will go to the side with lesser gaseous molecules because you are doing Le Chatelier principle there. So what we can say is 4 moles of gaseous reactant. I think a lot of people, they forget that. They just say 4 moles on the left, 2 moles on the right. That is not correct because pressure affects gases the most. So 4 moles of gaseous reactants versus 2 moles of gaseous products. So at higher pressure, the equilibrium will shift to the side with lesser gaseous molecules. So 2 moles of gaseous products. Higher pressure, shift the equilibrium or shift the reaction to the side with lesser gaseous molecules, which means in this case it's going to favor to the right hand side. So therefore we get more yield of ammonia. So yield of ammonia will increase at higher pressure, the rate will be faster. But with temperature, because the flow reaction is exothermic, when you go too high of a temperature, the equilibrium will shift backward and that will give you a lower yield of ammonia. So this, however, would also mean that the reaction will be very slow if you go lower temperature. So in the compromise, the best compromise between the rate, the low yield of ammonia, as well as the getting a fast enough rate, you come to this compromised temperature here. But that doesn't apply to pressure because high pressure will both favor a faster reaction as well as a higher equilibrium yield of ammonia. Those are all the idea about rate and equilibrium for temperature as well as for pressure. This is a very famous essay. The 2 marks are for temperature, 2 marks are for the pressure, and that can be broken down into 1 for the rate and 1 for the equilibrium, or how much you get for the yield of the product. Now, one of the major uses of ammonia is used to make fertilizers, obviously, and fertilizers are used to improve plant growth. All those nitrogen, phosphorus, potassium, nutrients required by the plant. So now, what do you want? You want ammonia reacting with H3PO4, but very specific. You want from diammonium hydrogen phosphate, which the formula has been given there. So you have ammonium and you have HPO4. If you can imagine H3PO4, when you lose a H plus, you're going to get H2PO4 minus. And then when you lose another H plus, you're going to have 1 H remaining and then PO4, 2 minus. And then when you lose another H plus, you will get the phosphate ion, PO4, 3 minus. So going back to this is the one with 2 minus charge, because there is 2 ammonium, which is 2 of that plus 1 charge. You will also produce, nope, you won't produce water, because when ammonia acts as a base, it doesn't produce water because it balances out the atoms as this lone pair there, except the H plus. You accept 1 H plus, you become NH4 plus. You accept another H plus, you become another NH4 plus. So altogether, you just need 2 ammonia, and that equation should balance out. So 2 of the hydrogen goes there, become H plus, get 2 of the ammonium. Now this becomes HPO4, 2 minus, and this should be alright. They don't ask for step symbols, we are okay for that 1 mark there. Now explain this reaction in terms of Brown-Stirred-Lowry theory for 2 marks. So we need to say what is a Brown-Stirred-Lowry acid and what is a Brown-Stirred-Lowry base. So Brown-Stirred-Lowry acid is a proton or a H plus donor, as stated in the syllabus. We can see that H3PO4 donates 2 protons, donates 2 H plus to become HPO4, 2 minus. So there's your first bit of the definition, and don't know why you choose that same color. The second bit, Brown-Stirred-Lowry base is a proton acceptor. So if you accept protons, that means it's a proton acceptor. I guess both thing is the same thing. You could have said it accept proton, or you could have said it's a proton acceptor. it doesn't matter. I'm just trying to follow the same standard as I did in the previous question, really. No particular reasons. So the ammonia accepts protons. Each ammonia accepts 1 protons, okay, on its lone pair. On its lone pair of nitrogen to form ammonium ion. Okay, all right. Now part D. So the first question here really is all about eutrophication. So what we can say is eutrophication occurs. Eutrophication is a fixed essay you can prepare for. It's part of environmental chemistry, and it's basically this uncontrolled use of nitrate fertilizers, and they can get washed down into the river, especially during heavy rains, because all nitrates are soluble. If you think about your solubility rules, all nitrates, salts are soluble in water. This includes all those fertilizers which contain nitrate. So I've just talked about eutrophication. There's no way you can get all the marks just by talking about one thing. You know, the exam skills is all about contents. It's all about the points of interest. So for 3 marks, you need to have 3 points of interest. So if that's my first point, I need to describe what is eutrophication, because leading up to the severe reduction in water quality. So when that happened, then we get nitrate fertilizers will encourage. So when they get washed into the rivers, so when washed into river or lake, whichever one really, river or lakes, will result in severe growth or very rapid growth of algae on the water surface. So they grow on the surface. So what happened then is this will block sunlight, because they are blocking the sunlight to the water plants, to the aquatic plants or water plants, which cannot photosynthesize. If they cannot photosynthesize, they cannot produce food. If they cannot produce food, they cannot produce oxygen. So therefore, the dissolved oxygen in the water, in river water, drops or decreases, and as a result of that, aquatic animals will die. Aquatic animals die, the ecosystem is destroyed. So basically, the river is kind of ruined, the water quality is quite bad, and then when the animals die, a bacteria will infest on them, and you get a growth of bacteria, obviously. Okay, so the ecosystem get destroyed, something like that. Alright, so it's all about the rapid bacterial growth afterward as well. So rapid bacterial growth, probably I don't say the ecosystem get destroyed, perhaps I can say bacterial growth. Bacteria multiplies, bacteria grows as they feed on the dying animal. On the dead animal, not dying animals, on the dead animals, okay? So a lot of these points, you don't really need to follow word by word. It's basically essays which you need to know the order of events, and you can write in your own words, obviously. What next? Oxides of nitrogen are produced by the action of bacteria on nitrate fertilizer. Explain the problems, so there's plural there. And then release of oxide of nitrogen into the atmosphere. Include an equation, so you need to have at least one equation. So oxides of nitrogen into the atmosphere, this is about catalysis. This is about homogeneous catalysis in the upper atmosphere, where we have NO2 catalyze SO2 going to SO3. So they say something about an equation. So what we could say is NO2 plus SO3 plus SO2. The SO2 goes to SO3 in the industry as part of equilibrium process, and you need a catalyst and pressure and temperature. In the upper atmosphere, all of these are just gases. We don't put V2O5 in the upper atmosphere. Instead, the SO2 go to SO3, catalyzed by this NO2. So the NO2 get involved in the reaction. It give away the oxygen to the SO2. So the SO2 steals the oxygen. The SO2 get oxidized in forming the SO3. Having said that, the NO2 will get reduced because it has lost the oxygen. One of those cases, one of those really simple cases where you can use gaining and losing oxygen to think about what is happening there. Now this thing here, the NO, can be regenerated because a catalyst is not used up in a reaction. The catalyst is regenerated. Now what happened there? I know they say include an equation, but they don't say include the equation. So that means you can write more than one equation. These are the three general equations that go together, especially when you want to talk about the formation of acid rain as catalyzed by NO2. So this SO3 plus your rainwater is going to give you your acid rain, which is H2SO4. So having said that, what is the danger of this oxide of nitrogen? Well, we can see that the effect is that the oxides of nitrogen can catalyze the SO2 forming SO3, and the SO3 can cause acid rain, can form acid rain, and this acid rain that can destroy limestone buildings, that can destroy crops, limestone buildings, and obviously they can make river water really acidic as well and kill some river animals and stuff as well. So that's it really. The equation is probably worth 1 mark. Talking about the effect in terms of the NO2 forming acid rain that is possible. There's another answer that's possible here. I've only talked about the homogeneous catalyst where the NO2 is in the same state as the gaseous SO2 when they catalyze this whole process. But of course, you could have gone for the other option where the NO2 form acid rain. So you could have gone for just one equation. The NO2 plus H2O. This is a disproportionation reaction. So this disproportionation reaction would actually form HNO3, but that is not the only product it will form, and you will not be able to balance this equation unless you know the other product as well. So that is nitrite ion, and this is nitrate ion, nitrogen plus 5, and nitrogen plus 3, oxidation state from the redox topic. This is nitrogen plus 4. Changes in oxidation number must be balanced using changes in oxidation number to balance chemical equations. So you need 2 of that, and since the +1 and -1 oxidation number changes get cancelled out, so 2 nitrogens, and I have 4 oxygen, and I have 5 oxygen. 4 plus 1 is 5 oxygen, 2 hydrogen there. This equation is going to be balanced like that, provided it's a disproportionation reaction. So you could have written down this equation, disproportionation reaction, and then obviously you can say that the oxide of nitrogen can form acid rain, and this acid rain can destroy crops and limestone buildings and whatnot. So this is NO2 catalyzing the SO2, giving SO3 that can go on to form acid rain. This is NO2 dissolving in the rainwater to give you the acid rain itself. Both of them could be accepted as the problem associated with this oxide of nitrogen to the atmosphere. In hindsight, this is probably more direct. I should probably have written this instead of this. There are some years where they say write a series of equations on how the NO2 can result in the formation of acid rain. Okay, so there should be cases when you need to use these, and there should be cases when you need to use these. In this particular question, either of which will be acceptable. We could probably have gone with this, which is a lot simpler. And that's it really for this 2-mark question, environmental chemistry there. And that concludes the 21 marks overall question there. So this third question here is about organic chemistry. So we have an undesirable 7-carbon chain hydrocarbon. Blah, blah, blah. There are 9 structural isomers. So what is meant by structural isomers and what is meant by chiral center? There will always be marks and definitions. If I were you, I would list down all my AS and A-level chemistry definitions, just like with chemistry, biology, physics, whatever. And then you should prepare this list of definitions in your own booklet, in your own notes, so that you can review it as you need to from time to time, instead of reading, you're actually reviewing it again and again to consolidate your memory, and you have better retention. So structural isomers, from the name itself, they are molecules or compounds with the same molecular formula. There's the key thing. They must have the same molecular formula. So that means they have the same actual number of atoms in the molecule, in one single molecule. But what is different? Because of the name itself, they must have different structural formula. When you write out the structural formula, they looks different because they are structural isomer. As for chiral center, you're looking at a carbon atom, and this carbon atom is bonded to 4 different groups. 4 different groups, well, in fact, 4 different atoms or groups of atoms, because it could be just atoms or it could be groups of atoms. I guess 4 different atoms or groups should be okay, and therefore you will get non-superimposible mirror images of each other called enantiomers. Now, what are the structures and the names? They don't mention what kind of formula they want. You could give displaced, you could give structural, you could give skeletal. If it were up to me, I would always go for skeletal first, because this is the fastest one and this is the most elegant one that you need to get used to. No matter how much you hate it, you have to learn until you can do it properly, because in A2, there's no way you would draw display for such a big molecule. I mean, C7 is still okay, but sometimes you get rings and other big molecules where it becomes almost impossible. So master your skeletal whether you like it or not. Now you want structural isomers of C7H16, and you want this contain a chiral center. So you're not asked for every single isomer. So if I were you, I would start off from 1 carbon like that, and then I would draw 2 carbon like that, because 1 carbon, 2 carbon. Now I'm going to draw 3 carbons, 1 carbon, 2 carbon, 3 carbon, 1, 2, 3, 4, 5, 6, 7. And I have a hydrogen there. Carbon from 4 bonds, 1, 2, 3. There is a hydrogen there. So that means this is a chiral center there. And if I'm asked to name these, so I mean, I already gotten the structure, I just need to name it. Then I will look for the longest chain carbon. That would be alright, but if you are thinking about the other way around, the pink one will not be alright, because the 4, the branch group is at position 4. 4 is bigger than 3, so pink one is not correct. You want the lowest number for the branch there. So what we get must be 3 methyl, because your side chain is a CH3 methyl branch, and 6 carbon is hexane. Now we also want a chiral carbon for the other one. This one is the starting point for you. You can't do anything on this 1 carbon and 2 carbon. But when you have 3 carbon straight chains, you know you can branch it further. So I'm going to draw this 1 carbon and 2 carbon the same way. I'm going to branch out. So straight chain, and then I'm going to do a branch chain. This is called chain isomer. So instead of that 1, 2, 3, I'm going to do a branch like this. So this 3 carbon is now a branch from this 3 carbon straight chain there. Onto my numbering, 1, 2, 3, 4, 5. Well, you could be thinking of that, or we could be thinking of, let's say, the green color one. 1, 2, 3, 4, 5. Where is our branch now? If I go the blue color one, as I did before, 3 and 4 is my branch, 3, 4 dimethyl. If I go the green color, 2, 3 dimethyl. 2 and 3 are smaller than 3 and 4. So obviously the blue color one is no longer applicable here, as that does not give you the lowest numbering possible. This is 2, 3, and they are both dimethyl. They are both methyl. So now I have 2 methyl, it's called dimethyl. They are at position 2, they are at position 3. And my longest carbon chain now is 5 carbon. So my longest chain is now 5 carbon. It's called pentane there. On to the next question, write an equation. That means one equation. They don't say the equation, which means there could be one. Could there be more than one answer? No, there can only be one answer, right? Because complete combustion will give you just CO2 and H2O. So heptane was C7H16. Forget the formula. Well, have a look at here. C7H16, that is CnH2n plus 2. General formula of alkane homologous series back there in O-level GCSE or IGCSE level chemistry. So do not get this thing wrong. Plus O2, and you get complete combustion, so CO2 and H2O. 7 carbon there, so you will balance with 7 CO2, 16 hydrogen there, you balance with 8 H2O. Now you have 8 oxygen, and you have 14 oxygen plus 8 oxygen is 22 oxygen. 22 oxygen, and you have a molecule. You cannot change these 2 at the bottom. You must have 11 O2 like that. Now part 2, you want incomplete combustion. Incomplete combustion could give you multiple products. They could give you carbon monoxide. They could give you carbon soot as this black solid. But then they want specifically a solid pollutant. A solid pollutant. So you're looking at the formation of carbon. But you could also produce carbon dioxide or carbon monoxide. So let's just try and balance our equation. So that means not enough oxygen. Basically, incomplete combustion means not enough oxygen. I'm going to just produce carbon first. But they don't say you cannot produce any other thing. So I'm not sure if I can balance my equation if I just do like this. If I have 7 carbon, then I have 16 oxygen. I can never balance it because, can I? Well, actually I can. 7 carbon and then 16 hydrogen. So 16 hydrogen, 8 oxygen. Then I'll have 4 O2. Or you could have other equation, other possibilities, where you have lesser carbon produced, but you can produce CO or carbon dioxide, etc., etc. As long as the equations are balanced, as long as you have a solid pollutant, the carbon soot there. Incomplete combustion can also lead to emission of unburned hydrocarbon. Because you don't burn completely, as you don't have enough oxygen. What is the danger of unburned hydrocarbon? This is a very specific thing of unburned hydrocarbons. So the danger is on unburned hydrocarbon that can cause photochemical smoke. So this is a photochemical smoke like in Beijing, which has a lot of industry obviously, and this thing can result in breathing problem or respiratory distress. But the idea is the photochemical smoke, and it can cause breathing problems. Now part C is about free radical substitution mechanism, and you need the presence of UV light. You get a wide variety of products. That is why this is called a chain reaction. It's like nuclear reaction. You can't control it because it's very reactive. Radicals are very reactive. Propagation especially is quite hard to control because it just spread everywhere. Propagation there. So what we're going to be thinking about, name the mechanism. The type of reaction is substitution, stated in AS introductory, all the terminology. Type of reaction is substitution. The mechanism is called free radical substitution. The next bit obviously want you to write out the mechanism step by step, and you got to include the names of each stage. You got to describe the mechanism. Instead of using a lot of words, try to write the equation correctly. You have 5 marks, so we got to write a lot of equations as well. So the first thing that will happen is initiation. So in the initiation stage, the Cl2 breaks by homolytic fission. Homolytic fission is a term stated in the AS introductory chemistry syllabus. Basically, the covalent bond breaks equally so that you have half-headed arrow. You don't use a full-headed arrow because it's not 2 electrons, it's 1 electron. 1 electron goes there, 1 electron goes there. And this only happens in the presence of UV light, and you will get radical. So breaks by homolytic fission to form chlorine radicals. So these are called radicals. Species with unpaired electrons are called radicals, definition of which is stated in the AS atomic structure topic as radical definition there. And then revisit these under introductory organic chemistry as well. So the next thing will be your propagation. So propagation comes from the English word to spread, okay? So radical reacts with molecule. So molecule has no charge, it's not radical, to form another radical, and then another molecule and another molecule. So you must have radical on the left and you must have radical on the right. That is the idea of propagation. So if I have one of these chlorine radical and I react with C7H16, the first product I'll get will be HCl, as it takes away the H from there. And when this loses a H, the C7H16 will lose a hydrogen. I now have C7H15. I must have a radical. I'm not saying the dot, the radical is on the hydrogen, it's actually on the carbon when you think about it. And then we cannot stop there. Propagation, you need to show at least 2 steps because you haven't gotten to the product in the propagation step. This is the product that you want. This is a single substitution when you replace one hydrogen with chlorine. This is an overall reaction. It's not the mechanism. The mechanism is what happened in detail. So I still have to show C7H15 dot. So I have my radical C7H15 dot. I react it with a molecule, another molecule of Cl2. Molecule is not radical. So then I would form my molecule, which is C7H15Cl. No longer radical because I pick up the Cl radical, and then the Cl2 will form me another radical. Radical plus molecule give me molecule and no radical. Essentially radical on the left, radical on the right. Okay, you form a different molecule, you form a different radical. Last but not least, you have something called termination. So initiation is going to be the slower step as you need to break bonds without forming anything. Highest activation energy, you need the UV light to initiate this process. In termination, what happens is radicals recombine. This is the key idea in termination step, recombine to form a molecule. So that means radical and radical, and then no radical. It's the opposite of initiation. It's the fastest step because you are forming covalent bond without breaking any covalent bond at all. So what we get is things like Cl dot and then C7H15 dot. So I could probably write like this, but then I will have C7H15 dot plus Cl dot giving me C7H15Cl. So radical and radical recombine to give me no radical there. That is termination step and the end of the 5-mark mechanism question. In this question, we have organic chemistry involving ethanol. So ethanol is this CH3, CH2OH. If I start drawing things in skeletal, I will be better equipped once I draw it out and I can see what is happening there. Carbon from 4 bonds, so there's CH3 there. Carbon from 4 bonds, 1 and 2, so there is 2 hydrogen there. We always show hydrogen bonded to oxygen or nitrogen. It's only the hydrogen bonded to carbon that don't appear in the skeletal formula. CH3, CH2Cl, so again, carbon from 4 bond, there is 3 hydrogen there. Carbon from 4 bond, 1 and 2, so there's 2 hydrogen there. And in this reaction 1, we are going from left to right, so we have replaced or substituted the chlorine with OH. This type of reaction, oops, I don't know why I spell it wrongly. Type of reaction is going to be substitution. Type of reaction is not mechanism. Mechanism is not type of reaction. Make sure you know in introductory organic chemistry syllabus, type of reaction, all the terminology are stated there. Going from 2 to 1, we have replaced the OH with Cl. That is also, I don't know why I keep on writing it like that. That is also a substitution reaction. We have replaced one group with another. In this reaction 1, you can also traditionally call it hydrolysis because specifically we are hydrolyzing the CCl bond and becoming COH, and we're doing it in the presence of water because we are using aqueous and OH. So we can also know this reaction 1 as hydrolysis. In this further up reaction on the right, you are distilling, you are heating it actually, heat and distill by the way. Heat and distill immediately with this acidified dichromate 6. So this is chromium plus 6 oxidation number, minus 2 overall oxidation number, 2 chromium plus 7 times minus 2 for the 7th oxygen, each of which is minus 2. You should know that 2 chromium minus 2 plus 14, 2 chromium is plus 12 there, each chromium is plus 6. This is your orange color oxidizing agent, and when they react as oxidizing agent, you're going to go to chromium plus 3 in this chromium 3 plus aqueous, and there is your orange to green color observation as oxidation of the primary alcohol. Because the carbon bonded to the OH is bonded to one other carbon, there is 2 hydrogen there. You can lose the hydrogen on this carbon with the OH. Loss of hydrogen is going to be what you call oxidation. Actually, it's an overall redox reaction because the oxidizing agent will get reduced as it oxidizes the alcohol. So if you write down redox, it will be okay as well. But usually when we say oxidation, what we mean is oxidation of the alcohol, reduction of this oxidizing agent. And when you heat and distill immediately, you are not going to go all the way to the carboxylic acid. You're just going to stop at aldehyde, which is 2-carbonaldehyde. You named it as ethanol. On this far left hand side, you have halogenoalkane, and here you're using NaOH, but this is not aqueous conditioned. So this is in ethanol. This is not in water, meaning to say it is not aqueous. This is a classic type of question where you have substitution versus elimination. If you have no idea what I'm talking about, you should check out my topical playlist under halogenoalkane chemistry. There's something called substitution versus elimination. In there, I outlined, well, in fact, compiled a couple of past year paper questions from my yearly tutorials on places or on occasions where they talk about substitution versus elimination, such as this particular case study. I can tell you that examiners, whatever curriculum, 16 to 18 years old chemistry, they always like to ask you substitution versus elimination. This one is using aqueous NaOH. This substitution there is also known as hydrolysis. As we are talking about halogenoalkane chemistry, we are breaking the CCl, becoming COH. That is aqueous NaOH and reflux. This is NaOH in ethanol. So this is NaOH in ethanol and reflux there. Okay, so there's the main difference there. The use of the solvent. The use of different solvent is going to favor one reaction over the other. Now the first question, give an equation for reaction number 2. Reaction number 2 is from alcohol to the halogenoalkane. You need the reagent. So in order to go ROH to alcohol halogenoalkane, we can use CH3, CH2OH. My usual favorite reagent is PCl5, at least on paper. It's not as easy to handle in the laboratory, obviously, quite dangerous, yeah? So CH2Cl. And what happened with the PCl5 is it will chlorinate the OH, and this OH comes off, and the oxygen go to the phosphorus, the hydrogen combine with one chlorine, you will get HCl, and you get POCl3. That's the overall reaction. There is alternative for this reaction. If I just write it on top here, you can also use SOCl2. That is called thionyl chloride, SOCl2. You can also chlorinate the OH with Cl. So that's the first thing I will form. I take out the OH, the H combined with the Cl. In both of these reactions, which are very, very exothermic, you will do this at room temperature. Whether you use SOCl2 or PCl5, you do at room temperature. You get steamy white fume of hydrogen chloride gas. It cannot be hydrochloric acid because it's a gas. Hydrochloric acid is aqueous solution. That's the definition of acid, dissolved in water. And of course, the other oxygen goes to the SO there and give you SO2 gas. There are other alternatives, of course. You can use hydrogen chloride gas, HCl gas, reacting with these, and you can potentially substitute that out and you get water. What else can I say? State the reagent and conditions required for reaction 1. Reaction 1, as I mentioned, is a substitution of Cl with OH. You also know this as hydrolysis. Hydrolysis substitutions versus elimination. This is in aqueous and OH. Aqueous, they mean in water. So your NaOH is in water in aqueous conditions. So we need NaOH. If I do bracket aqueous, without this aqueous, you will not get the marks. If you say NaOH in water, it is fine. And you have to reflux this reaction, just like you have to reflux for the elimination to happen as well. Identify the organic product X. So this is elimination. Elimination is going to remove the hydrogen from the adjacent carbon, from the carbon next to the carbon with the chlorine. So what you're going to get will be an alkene plus HCl. So your alkene is just ethene. They say identify, they don't say formula, they don't say name. I could give the formula, CH2 like this, structural formula. I could give ethene. The question didn't specify which one, so you could get away with either of these two. The next one, nitric acid is added to these products of halogenoalkane plus NaOH in ethanol. What would you observe? What we get here is in ethanol. So we would kick out HCl, as I mentioned. HCl like that, is that correct? Yeah, you will kick out HCl, but then the HCl is acidic. Acid will react with the base. Acid will react with the base, and what will happen is instead you get NaCl and you get water, because the HCl product will react and get neutralized by the basic conditions, NaCl plus water there, and also give you alkene. But what is interesting is you have Na plus and also Cl minus. When you add acidified silver nitrate, so this is the acidified, and then silver nitrate, all nitrates are soluble in water. Silver nitrate, as you have used since 14 to 16 years old, O-level, GCSE and IGCSE level chemistry, you will get a precipitation reaction. As you know, when you react these two together, you will get the insoluble white precipitate of silver chloride, and then the other thing is also soluble. So this is not the ionic equation. This is the full equation, so this is not ionic equation. What is more common, however, they usually like to ask you to write an ionic equation. There will be Ag. Actually, that is the next bit of the question. Let me answer the next bit first. They're going to ask you to write Ag plus aqueous plus Cl minus aqueous, and that gives you the precipitate, the white color precipitate of silver 1 chloride, because this Na plus and NO3 minus, they are spectator ion, year 9 chemistry under balancing chemical equation. So what you would observe is a white precipitate forms. You cannot use PPT because you are not in a practical papers. In a theory paper, I don't think you're allowed abbreviation at all. Last two bits of this whole paper, identify the organic product that was distilled out. If you look at the formation of wine, as mentioned earlier, it was about heat and distill with oxidizing agent. Oxidation of primary alcohol could give you carboxylic acid if you reflux it, but it will give you aldehyde if you heat and distill immediately. So Y is ethanol, or this thing CH3, CHO. That is how you will write the structural formula of an aldehyde, showing the CHO there. Again, identify, so I could write the formula CH3CHO, or I could give the proper name. The name will end with Al, it's called alkanal. There's the family of aldehydes there. For these last 3 marks questions, seems like quite generous. We're going to be thinking about properties of and also intermolecular forces in the alcohol, as well as the aldehyde CH3CHO. We know that in aldehyde, we just have permanent dipole, because even though we have electronegative oxygen, you do not have hydrogen bonded to the electronegative oxygen. How can you get hydrogen bond between this molecule and another molecule of these? You simply cannot get hydrogen bond formed between them. There is only permanent dipole. When you have alcohol, so obviously, you have hydrogen bonded to the electronegative atoms. You can get, well, you can sketch it out if I want to. So like that, and then I have lone pair on the other alcohol, so like that, and then the lone pair forms a hydrogen bond to the delta plus there. So delta negative, delta plus, dipoles, lone pair on the electronegative atoms. Between the alcohol, there is something called hydrogen bond there. Of course, that is not the actual answer to this question. This previous bit was asking ionic questions, so I better not encroach too much into that space there. So explain in terms of the properties of and intermolecular forces. And the last bit is why this condition ensure or make certain that you collect aldehyde and not the alcohol or carboxylic acid product. So what's happening there is I can say CH3CH2OH can form hydrogen bond between its molecule. And then I also need to mention between the aldehyde CH3CHO, which is product Y, can only form the weaker permanent dipole between its molecule. Both of them are in addition to van der Waals forces, London dispersion, because both of them contain electrons in the molecule, obviously. So I'm not talking about the van der Waals here. But hang on. They did mention intermolecular forces, so perhaps I need to mention the van der Waals forces as well, just in case, because we want to be as complete in terms of the intermolecular forces as possible. So, and van der Waals, which is to do with the London dispersion. If you want, you can use London dispersion, or you can use the term van der Waals forces. All right. Now onto the next one. So we know that the aldehyde can only form permanent dipoles in addition to van der Waals forces. So it seems like I'm running out of space because I've written down both van der Waals and London dispersion forces, but it doesn't matter. Now we can say that therefore the CH3CH2OH will boil at, well, in fact it is the aldehyde that will boil first. The CH3CHO will boil at lower temperature. As I already talked about the weaker permanent dipoles, and this one can form the much stronger hydrogen bond compared to these weaker permanent dipoles. So CH3CHO will require lower energy to break the intermolecular forces. They will boil at lower temperature, therefore will distill out first, because the one with the lower boiling point will vaporize first, and once it vaporizes, it will get condensed out from the condenser, the sideway condenser. It will distill out first instead of the alcohol. Instead of being oxidized further to carboxylic acid, and the alcohol will not be collected first because the alcohol will have a higher boiling point due to the formation of the stronger hydrogen bond there. So overall, I mean, that's the whole idea why this heat and distillation works, in order to ensure that you get the aldehyde, because it will have a lower boiling point. Once you form it, it will vaporize first due to its lower boiling point, and you will collect it from the sideway condenser upon condensation of the vapor, and that wouldn't be oxidized further to carboxylic acid, because when you form it, it will be escaping on the side. Reflux apparatus does not have the sideway condenser. Your condenser setup is vertical, so your vapor cannot escape and condense down. In fact, it gets back into the flask, and they get further oxidized when they come into contact with your oxidizing agent. Reflux will ensure that you get carboxylic acid. Heat and distill will ensure that you stop at the aldehyde stage there. And that's the 3-mark question there. And that's the total 11 mark for this organic chemistry question. And that's the end of this whole paper 2-1 for the October-November 2015 series. So don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. Thank you for your support, and do spread the words about the channel if you think it has helped you. Perhaps it can help a lot of other people as well. See you in the next tutorial video.